And then we start with nothing but our same small example. Nodes 1, 2, 3, 4 with 6 directed links. Now we already know the answer, but we're going to now derive that answer using a matrix notation. And in the rest of this course, we will see quite a few other matrices, especially around lecture 8. All right, so the very first matrix we'll construct to represent this graph is a matrix we denote by H. Before we define the ijth entry of a generic matrix H for any general hyperlinked web page graph, let's just look at this specific example. I'm going to define the corresponding matrix H, which is 4 by 4, because there are 4 nodes, as the following. Look at node number 1. That will give me the first row of this matrix. Number 1 is pointing to number 3 and no one else. So I want to capture that information. So 1 doesn't point back to self, 1 does not point to node number 2. Let me just label these columns and rows. But it does point to node number 3. It does not point to node number 4. See, just by writing down zeros and ones in this row, I am encoding, representing the graph, at least part of the graph. Okay, what happens with node 1's outgoing links? Now, you may remember we also want to normalize by the number of outgoing links. Well, it's actually already captured here. There's only one non-zero entry here, so the number of outgoing links is 1. Now, we could write 1 divided by 1, which is 1. Okay, that's fine. What about node number 2? Well, by symmetry, it's actually the same as node number 1. So 0, 0, 1 over 1, 0. This 1 is an indicator to indicate that, hey, there is a link from node 2 to node 3. This 1 is a counting variable. It says, I count there is only one link coming out of node 2, pointing to some other node. So actually the function of this 1 is not the same as the 1 in the denominator. What about node number 3? Well, it only points to 4, so you know the answer, 0, 0, 0, and then 1. Divide by 1. What about node number 4? Now, this gets more interesting. 4 points to all the other 3 nodes except itself, so this is 0. So you can see the diagonal of this matrix 0 because no node points back to itself, but points to everyone else for node 4. So we have to write down 1, 1, 1. Now, we can just write it as such, but to make the computation easier to carry out, we're going to incorporate this normalization right within the definition of this matrix H. We say, since there are 3 outgoing links, let's represent the normalization by dividing each entry with 3. So we got 1 over 3, 1 over 3, 1 over 3. Now, you can see immediately that every row of this matrix H sum up to 1. Okay, well, that's by definition, by design of this matrix H. We constructed such that it sum up to 1, unless this node points to no other web pages. We'll come back to that in the next module of the lecture video. Okay, for this graph, we are fine. Okay, so you may have a lot of zeros, which is actually the real case because the real web is very sparse. And then you have non-zero entries, which are actually identical. They are basically all just 1 divided by the number of outgoing links. And then, of course, obviously, they'll sum up to 1 per row. This is how we construct this matrix H. You say, what's the point? I mean, I can see you are capturing the connectivity pattern of the graph algebraically in a bunch of numbers in a matrix. But why? Why would you want to do that? Well, because this will facilitate, accelerate our discussion. For example, now when I say I want to write down the relationship of these nodes' importance scores, for example, okay, pi 3 equals pi 1 plus pi 2 plus pi 4. Okay, over 3, because pi 4 is split across 3 ways. I can write this down by staring at the graph. But of course, when the graph becomes big, for a computer to stare at it, is actually staring at an algebraic representation of the graph. Okay, that gives you everything you need to know about the graph. And as you can see, what's happening is the following. Just look at this column, not the row. I know we constructed the graph row by row, but now look at each column. It says that pi 3 really is pi 1 plus pi 2 plus pi 4 times 1 over 3. In other words, if I give you a row vector, pi 1, pi 2, pi 3, pi 4, and I ask you to multiply with the third column of this matrix, which is 1, 1, 0, 1 over 3. This is what you get. Right? Pi 1 plus pi 2 plus pi 4 over 3. Aha! If that's the case, then actually, in order to compute these pi's, all I need to do is to multiply this row vector on the right by the corresponding column of this matrix H. So in general, what we can do is to say pi vector transpose times H matrix will give me the new pi. Okay. And what is this H in general? In general, this H is defined as the ijth entry. Could be 0. Okay, if I does not point to node J. But if I does point to node J, it is nothing but 1, well, normalized by the L degree of node I. That's the general definition of matrix H, which you can check is exactly what you got from this numerical example. So generally, you can define the ijth entry of matrix H as such. What's the point of doing that? The point is that then you can represent the linear equation through a matrix representation. Pi transpose times H equals pi transpose. Because of the manual observation, writing down this equation based on our try-to intuition is now entirely captured in this representation of multiplying pi transpose on the right by matrix H. Okay. Because we are multiplying this row vector by the jth column of matrix H to get pi j. All right. So now you say, hey, we're done. Well, there are two issues. A, it turns out that this matrix H doesn't always give you the existence of a pi that can satisfy pi transpose H equals pi transpose. And that's problem number 1, and we're going to tackle this in the next 2 modules of the video. Problem number 2 is that what about the computational load, even if for a certain graph this H suffices? What's the computational load to compute the eigenvector of a matrix, say H? Well, if you use MATLAB or C or whatever language you use, you say, hey, that's not too bad. Okay, that's assuming H is not too big. But if H, it doesn't even have to be 60 billion by 60 billion. If H is, let's say, 100,000 by 100,000, 100,000 relevant web pages to a popular search term, then computing the eigenvalue is a very intensive job. So Google need to do this real fast. How can we do that? It turns out that you can do it in an iterative fashion. Now, back in lecture 1, when we talk about distributed power control, it was an iterative algorithm too. But it was iterative back then because no one has a global view of the network condition, of the direct and interference channel gains. In this case, lecture 3 now, we also use iterative algorithm in Google's web page ranking method, but this time it's because the computational load would be otherwise too big. And back in lecture 1, we not only used iterative but also distributed. That's why there's a letter D here, because we cannot afford a centralized computation. In this case, however, we can afford a centralized computation. So both DPC and Google's ranking algorithm are iterative algorithms, but one is distributed computation, the other is centralized computation. Now, towards the end of the 4th module of this lecture, we will come back to this iterative method. You're going to compute the pi, not directly by computing the eigenvector of matrix H. But instead, you will keep multiplying pi transpose on the right by H. Call this the first iteration. Then that gives you pi transpose the second iteration. Now substitute this pi back here, then you get the third iteration, fourth iteration, and so on and so forth. Now matrix multiplication is not a simple job computationally speaking either, but at least this is each step of this iteration is much lighter load than computing directly the eigenvector. And if this can converge quite fast, then we have a computationally efficient way for Google to compute pi and thereby rank the web pages. So now we have two issues at hand. One is that this matrix H captures most of our intuition, but not quite. Turns out we need two modifications to ensure the existence of pi. Second, we need to efficiently compute when such a pi exists. So the rest of this lecture we will focus on these two issues until we get to the point where there's matrix G, the Google matrix, that leads to a guaranteed existence of pi and efficient computation of pi through this iterative method.